Right, well, it's a good job they asked me to do this part of the talk because it's the only thing in the talk that I would be familiar with. I'm going to talk mostly about air tightness issues, thermal bridging issues and insulation issues. And I'm going to do this pretty quickly because we're going to run out of time. 2011 changes to Part L. There's a slight change to the testing regime, which I'm just going to mention. And then there's a change to the maximum allowed permeability, which has already been mentioned. Unfortunately, for the existing dwellings, there's no real change, and I find that's a big shame. So if you look very quickly at the testing regime in the new and the old regulations, they look much the same, but if you look at the paragraphs that follow that, if you're going to use in your deep calculations a value better than the backstop of 7, you actually need to get each dwelling tested, which is a change. So in a sense, if you're going to do anything that's any way energy efficient, you're going to end up testing every dwelling. Yippee. Now, so previously it was 10, and now it's going down to 7. Is that hard to achieve? Well, first of all, I'm just going to say that if you look at the numbers, they're all meters cubed per hour per square metre, so let's not get confused between units. I'm going to call this the Q50, and this is the unit we use in the building regulations. For those of you who are involved in passive houses, the unit is slightly different because it's based on the air change rate of the building, rather than this one, which is based on the envelope area of the building. So is it difficult? Is 7 difficult? Well, all new dwellings that we've tested this year so far, the average is 3.63. And overall tests since we've ever started testing, it's 5.53. We do a good bit of passive house and Enerfit testing. If we take them out of the equation, you're at 6.4. So 7 is very average. And just looking at the previous slides where there was quite a lot of non-compliance due to air tightness, if you get the builder on board, if the builder's on board from the word go, you'll easily reach 5, 4, 3. And if they've got any kind of brain at all, and if they're on board, you'll reach those limits. There'll be no problem at all. I find when I go out, there's two main approaches. There's the room-by-room approach, and there's the envelope approach. So the envelope approach would be looking at the envelope of the building. In this case, the red line, more or less, going around the entire perimeter of the building here. And you'd be designing, from the design stage, you'd be thinking, where's my airtight envelope? The room-by-room approach doesn't really bother about air tightness until you get to the stage where you might have to test, and then you end up sealing room by room by room by room, which means that you have plenty of air tightness access points in all of these intermediate floors, joists, areas, and down through partition walls, etc., etc. So using the room by room approach, I typically find that good builders can still get down to about 3, but it seems to level out at about 3. So just to give you an example, this is quite an old slide, one I have since 2008. Using the envelope approach, a passive house getting down to Q50 0.45. A moderately good builder was a self-built, they got down to 5.2. And the reason why I think testing of renovations maybe or extensions is important, 26. So these people were colder after spending a lot of money on a renovation than they were before the renovation. And there was absolutely no doubt as to why when I went in, it was because there was no air tightness at all. In fact, anything that had been airtight was now ruined. And I've seen that several times since then. So what are the problem areas? What are the common defects? In no particular order. Usually what I find, it's unsealed masonry, unsealed joists for intermediate floors, poor windows or poorly fitted windows. Although I must say people often blame windows when windows aren't the worst thing at all. Double doors and sliding doors are often weak around pipeworks, attic hatch doors, suspended timber floors, electrical fittings, poor airtightness, membrane fitting if you have one, and on and on and on, until you're blue in the face. So here's an example. This is a house I tested last week, a brand new house somewhere in Dublin. And it looks like all the rest of the houses because it had to fit into the general scheme of houses in the area. So when I turned up, we just set up the fan and did a quick test, and it came in at 7.15. So well inside the building regs that it has to achieve of 10 or less. But if it was going for the 2012 regs, it would be slightly above what was needed. We found quite a few leaks under window boards, basically coming straight in under the window and under the window board and around radiator pipes. So they were all sealed up. And in a couple of hours, they had 5.5, and I was left to go home, and that was fantastic. Now, you probably can't really read the numbers. If you can, it's great. But this little device is an airspeed measuring device I use a lot. You find leaks with it. You can measure how bad are the leaks. So if you see this in a picture but you can't read the number, don't worry, it just means there's a leak there. So this is in this particular house, even though they were at 5.5, they still had leaks coming in everywhere because there was no air tightness strategy at all. It was just, oh, we'll find leaks, right, we'll bung them up now quick. So there was still air coming in around the back panel, behind the shower, door architraving upstairs, around the window where the windows are butted together. The skirting board, 2.3 metres per second. So if you can see that figure, for example, in 1 second in test conditions, that air has moved 2.3 metres into the room. It's quite a lot of air. The string of the stairs, 0.42, and through the floorboards upstairs, that's a small little leak, but still it'll come in. So basically everywhere. I could have another 15 pictures of different areas for that house. So if you're not doing an envelope approach and you're doing room by room, or you're not even doing room by room, your common failure areas are everywhere. Anywhere that there's a gap, a crack, a joint. Just some further examples from other houses. This is, if I go into a house that I'm testing and it's already finished, it's painted, everything is done, how do I find out if there's a leak through the floor? Well, you try and concentrate some of the floor, so you use a little, that's the top of a shoebox with a hole in it. You press it down into the floor covering, particularly if it's carpet, and it will concentrate the air in that area, and you can get a reading of the air that's coming out. You can use smoke tests. Smoke tests are good for finding leaks, not so good for really determining how much leakage is there. But that's a very good quality window that was still leaking. A very good quality door with a leak of nearly 2 metres per second coming in one of the joints. A very common building defect in this country, not only air but mice get in through these holes. And if that's a cavity wall, as that particular house was, it can get into the cavity and then it just turns up anywhere in the house. This is a window board to a window detail, 7 metres per second. So in 1 second that air is from me over to the boys over there. It's hideous really. And that's as bad as a leakage can be. It basically means there's nothing to stop the air coming straight in. And this is another skirting board effort. That's a block wall. Unsealed masonry is not airtight, so it's basically coming straight in 5 metres per second under that skirting board. And if you don't believe that masonry isn't airtight, here's another example where the insulation board stops the air from getting right through the blockwork. So once it gets to the insulation board, it has to kind of span out either side. And this is just getting a reading of the air that's coming out the sides of that insulation board. Now, there's a lot of talk at the moment as well, and especially in low energy building circles, about using OSB for your airtight layer. Can everyone understand my West Cork accent talking fast? Is that all right? So the OSB is an airtight layer. It's actually quite a good airtight layer, but if you're going for the really low results, you'll find that sometimes it's leaky. And in this particular house, he'd got down to a Q50 of 1, and we just couldn't find any more. So we stuck up a couple of square metres of plastic, and after about 2 or 3 minutes under test conditions, that's bulging out. So he's kind of stuffed really, unless he does something with his OSB. Now, that's very quickly on airtightness. On thermal imaging, 2 minutes, very good. On thermal imaging, you can see inconsistencies in the insulation layer and in any thermal bridges that you have, but it's not a requirement to do thermal imaging. I find it's very good for finding these kind of problems, but ideally we'd have much better building control than we have, because we wouldn't need to come around with the thermal imager afterwards. If you look at this wall, we're designing in or we're building in thermal bridges at the window reveals. For example, there's mortar snots on the insulation boards, so they'll never fit together properly. There's gaps where the boards just come away from the wall, and who cares anyway. Designing in thermal bridges, if you look at this lovely nice glazed area, but of course there's RSJs across the top and intermediate reinforcement bars, so when you look at that with the thermal imagery, you can see there, it's absolutely howling out because there's no insulation around these points. Here's a geometric thermal bridge where you've more heat loss area on the outside than the inside, and that's a typical Irish detail. You get these big triangles when you're doing thermal imaging where the geometric thermal bridge is just pulling extra heat out of that area. Whereas this is an example of good practice. It's a Poroton block house with good attention to detail, and if you look at the corner detail there's really no big triangle. There's nice straight lines, and that's fine. If you're eagle-eyed enough, though, you can see that there's recurring thermal bridges where the Poroton block mortar is is slightly less insulating than the blocks themselves. Here's another example of what you can use thermal imaging for. The developer in this case didn't trust that the builder had put insulation in the wall all the way up to the roof. Now it's a monopitch roof on the very top of that, so it's a full height ceiling inside. And if you manipulate the image, eventually you can kind of see pretty much there's a straight line across at the top of the windows. Now the thermal imaging doesn't tell you exactly why that's there, it just means there's something different going on. And in that case we ended up having to drill holes in the wall, and indeed exactly at that level there was no insulation. I have 2 more slides. This is a house where the owner was cold, and he was cold because there was no air tightness in it, but also if you look you can see the snow through the ceiling, for example. Several of the areas in between the joists and the rafters and everywhere had no insulation at all, and you can see heat coming out through the roof area there using the thermal imaging. Rather not do it, have it built properly first time, but if you need to, thermal imaging is very handy. So the last slide then is that same house, and it's a little bit, it's not very clear, a bit fuzzy, but after running the fan for 10 or 15 minutes, because the house had poor air tightness, air can get into all of those. This is the upstairs, so it's timber stud partition walls. Air gets in between those studs and comes down into the house. And how does that look like with the thermal imaging? It's an absolute mess. It's one of my favourite slides ever because it's so hideous. It really is. And unfortunately, I have quite a few like that. There you go. Thank you. Good meal, Margaret.